Welcome back everybody to Ask Why, where we take engineering challenges and technology and break it down and see what's under the hood of those types of technologies. Today we're going to talk about a new series that we're going to be starting, and we call that Capacitor Confessions, where we really dive into different capacitor technologies and take a deeper look under the hood of what those technologies are and where they're best used, and give you guys a couple of examples how those work in the real world. Today with me here, I got Peter Blais, our head of technical marketing, and as he is known internally as the resource of all technical knowledge in the world. So Peter, I'm so glad that you're online here with me today. When we talk about aluminum electrolytic capacitors, what is the first thing that actually comes to mind? Like, what is it?
Bulk capacitance.
Bulk capacitors.
Aluminum capacitors are the leading technology of capacitors out there for sheer bulk capacitance.
So when I started looking at a capacitor, I think we're starting a series, Capacitor Confessions, but what would be a good example of what a capacitor actually is?
Well, that's a really good question, and let me just ponder about that. So a capacitor really is think of it as a big storage tank of electrons, right? I mean, when we have electrical circuits and things are turning on and off and there's ebbs and flows, we need to have a ready supply available for all of the electronics to draw electrons from. And so we need to have a reservoir of them, a big jar of electrons. Sort of think of a jar of, when you go and get fireflies and they're buzzing around and you stick them in a jar. Well, a capacitor is kind of sort of like that. It's a vessel to store electrons, lots and lots and lots, billions and gajillions of electrons stored in a vessel. That's what a capacitor is. And it just happens that aluminum electrolytics are give you a vehicle to be able to store massive amount of electrons in a system that is effectively a very low cost system. And it can handle low voltages as well as very, very high voltages.
So I guess that's a good example. When you start thinking about a jar, the more lightning bugs I get inside, the brighter it shines. So.
The brighter it shines, that's correct. So,
all right, well, for those of you guys watching online, you can actually see a little bit of an example up here of what an aluminum electrolytic capacitor looks on the inside. So when I start using an aluminum electrolytic capacitor, what are the best applications to actually start implementing a capacitor like that?
So when we take a look at aluminum electrolytic capacitor, its objective is to store energy. And so we look at electrical circuits where we need to store bulk capacitance. The larger the capacitance value, the lower the frequency it will support. So let's think about that. Oh, and I also mentioned that it can handle low voltages and very high voltages. So one of the most common areas of applications for aluminum electrolytics is, right now we're recording this and we're using a computer to do this, right, Simon?
Yeah.
Well, that computer is being powered by electrons, correct?
Yeah.
All right. Now, where are those electrons coming from?
They come out of thin air.
No. So we're over here. We're in South Carolina, right? And I believe the utility company is Duke Energy, right? They're producing the electricity that is coming into this building and going to the outlet. From the outlet, those electrons are feeding into the power supply that is powering the computer. And that power supply, the very first stage of it is it needs to rectify the AC to DC. And that rectification stage, we need to hold up the voltage and keep it nice and stable. And guess what technology is the default to use there?
Aluminum electrolytic.
Aluminum electrolytic. That's absolutely correct. And the reason is that we need high voltage parts. So typically they may be about 450 volt rated parts, and they're put in parallel, several of them, depending on the size of the power supply. And their sole purpose in life is to keep the rectified voltage nice and stable so that the subsequent stages of that power supply are able to function efficiently and get the voltage to the level that's used by the computer.
So since we're already talking about using those products in an application. Let's say we have a power supply like we described. It's an AC to DC power supply. We have 1 kilowatt. I have gone after my rectification stage. Now I have my wobbly DC line, and I want to make sure I have a nice DC voltage at that level.
Mhm.
Why is aluminum electrolytic the right choice for that area?
Well, let's back up and break down the requirements. You just said we need a lot of capacitance because we want to have a nice stable voltage. You also mentioned it's going to be after rectification. So if we're rectifying, 110, 220, it could be industrial 440, 480, we need high voltage, right? And so when we look at different capacitor technologies, the two buzzwords I just heard were high voltage and big capacitance value. And so when I compare aluminum versus film versus ceramic versus tantalum, which are the main technologies out there, the only one that meets those basic criteria, high voltage and a large capacitance value. Oh, and also we want a power supply that's relatively reasonable size form factor, not too big. Well, guess what? The only technology that makes it is going to be aluminum electrolytic. And there's several variations of aluminum electrolytic. You've got the original technology, which is aluminum electrolytic. Then you've got, the industry came up with a new variant of this, which was a dry system. It's called an aluminum polymer. Those are used predominantly on lower voltage systems. They don't go up to really high voltage, so we can scratch that variation off the list. And then there's a hybrid system. It's actually called aluminum hybrid, which is both electrolytic technology and polymer technology combined in the internal system of the aluminum electrolytic. And that kind of combines the best of both worlds. So you get high voltage and low ESR. So those could be used, but they cost more money. And since we're talking about a power supply and ESR at the front end is not too critical, we're going to use aluminum electrolytic, which has been used in that architecture, oh gosh, going back probably 100 years. Actually, I got a little story to tell you.
Oh, really?
Yeah, I have.
I didn't think you were 100 years old already.
No, but I've got a grandfather.
All right.
Or had a grandfather, and he has a K-part.
Okay.
Or had a K-part, which is back then it was the high fidelity system of the era. Today we've got like fancy TVs and stuff. Well, back then they had a K-part, which was a record player, and it was an AM radio, and it had a number of other things, and actually it would play the old-fashioned 78 records. And I actually have that K-part in my house. It dates back to the 1920s. And if you open up the back, actually the back is open, you can see everything in it, and you look at the power supply and the amplifier circuit for back then the high fidelity audio, guess what's in there?
I'm going to guess an aluminum electrolytic.
Aluminum electrolytics, that's right. And I had to go in there and actually replace some of those because aluminum electrolytics don't last forever.
Well, that's actually a good point. So aluminum electrolytic lifetime, that's really one of the biggest concerns in those areas. So what can we do in our designs to ensure that we have the best lifetime in those types of products?
Well, let's back up and talk about lifetime, because there's a mechanism behind the lifetime. And we call it aging, or they dry out. And we talk about aluminum electrolytic, and the electrolyte that's used in the aluminum electrolytics is actually a liquid. It's a special formulated liquid to act as a dielectric, but also allow charge transfer between the surface of the anode and cathode foil, which is very, very important for the capacitor to function. Now, over time, what will happen is that this electrolyte is literally consumed by the capacitor. So it is consumed, and the reason why it's consumed is there is water molecules inside of it, H2O, and the critical part of H2O is the O2 part, or no, the O part of the H2O. And aluminum electrolytics, you have to have a dielectric, on both the anode and cathode foil, but the anode is critical. That is Al2O3, or aluminum oxide. And what will happen is the electrolyte will attack that oxide layer over time, especially if it's just sitting on the shelf not being powered. And when you power it up, there's electron charge transfer, and what will happen is you will regrow the oxide layer, consuming the oxygen that's in the water molecules of the electrolyte. So you split up the H2O, vent off the hydrogen, and use the oxygen to regrow the dielectric. When you do that, over time, you're consuming the electrolyte that's in the capacitor, and eventually it will stop operating as a capacitor. It'll just become two parallel, very distant plates of aluminum. So that's referred to as the dry out mechanism, and that's a function of temperature and the voltage applied to the part. So when you design a system, you have to understand what the life is of the part, what the temperature rating of the part is, and then there's some calculations you can do to determine how long that part will last before it literally wears out. In the case of my K part, it was after its end of life, and I had to replace them, and it works fine.
I guess that's one of the big benefits when you use the aluminum polymer instead, right? Because there is nothing that dries out in those parts.
That is correct. So the aluminum polymer has really two key advantages. Number one is it's a dry system, so there's no electrolyte, so there's nothing to dry out in it. There is a degradation mechanism. The polymer can oxidize over time, and when it does that, its ESR increases slightly. So there is a wear out mechanism of the aluminum polymers. However, it is a drastically longer process than the aluminum electrolytic. The other benefit is, of course, the much lower ESR, which means that you can get away with typically using smaller cap values depending on the frequency versus an aluminum electrolytic, because the ESR works in your favor for the amount of capacitance you calculate for the circuit.
So we're getting a little bit towards the end of the podcast, but I do want to ask you, what are some common pitfalls that we have with aluminum electrolytic capacitors?
So there's a few common pitfalls. Aluminum electrolytic capacitors are polarized. And the worst thing you can do to an aluminum electrolytic is expose them to reverse voltage or negative voltage. Because as soon as you do that, what happens is that you start separating the oxygen from the aluminum in the dielectric, and the dielectric fizzles down into nothing. The part shorts out, and then it will go poof. And you have no more capacitor, and you have a round circle smoke emanating from where it ruptured the can. So that's catastrophic. That's very bad to do. No reverse polarity on the part. Very bad. So that's one thing. The other thing that you want to be sensitive to is the voltage that you put onto the part. So you want to make sure that you don't exceed the voltage rating of the part. They do have surge rating voltages, but as a proper design process, you want to really apply the voltage of the part that's rated or less. Those would be the two most critical things. And then the last thing is that you do want to pay attention to the wear-out mechanism of the part, so that based on the parameters of the system that you're designing, predominantly the voltage and the temperature, you pick the right rating of part so that it doesn't wear out in the lifetime expectancy of your system.
All right, well, as you saw, the aluminum electrolytic capacitor really is the unsung hero of any type of power conversion. With all the bulk capacitance that you need in your designs, the aluminum electrolytic capacitor is definitely the right choice for you. You heard today here what some of the pitfalls are with temperature, with lifetime, and with capacitance that's in voltage rating, all those types of capacitors. So Until next time, we're going to talk about some more of our capacitor technologies, and we're going to dive a little bit into what those technologies are in the next couple of weeks. Next week, we're going to talk about MLCC. Until then, keep on asking why.